1.
Hi guys, today we're going to talk about Graham's law. This is our last gas law for this unit. Graham's law states that the rate of diffusion of a gas is inversely proportional to the square root of the gas's molar mass. We can also apply this gas law to diffusion of a gas. So let's define diffusion and compare it to effusion. Diffusion is the tendency of the molecules to move towards areas of lower concentration until the concentration is uniform throughout. So gases will diffuse in a large open area, sort of like if you spray air freshener in a room. The particles, due to their own kinetic energy, will spread out and mix throughout the area. Now, during the process of effusion, gases tend to escape through a tiny hole in a container, like a nail hole in a tire or a pinhole in a balloon. Let's look at an animation of effusion and diffusion for just a moment.
Diffusion is the process whereby molecules of gas move to completely occupy a space, giving a uniform partial pressure. In this example, gaseous ammonia and hydrogen chloride diffuse through air from either end of a sealed tube. When the two gases meet, a precipitation reaction occurs, forming ammonium chloride. The mass of the hydrogen chloride molecules, relative to those of ammonia, is greater. Thus, hydrogen chloride molecules travel more slowly.
Now let's look at effusion.
Effusion is the process of gaseous atoms flowing into a vacuum through a hole in a container. The rate of effusion of gas molecules at constant temperature and pressure is inversely proportional to the square root of the molecular weight of the gas.
Okay, so let's go back to our notes. So you just saw an animation of diffusion and effusion. Both processes involve the movement of a gas. Diffusion occurs in a large open area, where effusion occurs as the particles move out of a small pinhole or opening. Now, the gas law that allows us to calculate the rates of effusion or diffusion of a gas is called Graham's law. One thing you would need to understand is gases of lower molar mass diffuse and effuse faster than gases of higher molar mass. That's because the lighter gases have less mass to carry, so they're going to move much faster in an open area. Now, the gas law itself is written as the rate of gas A divided by the rate of gas B equals the square root of the molar mass of gas B divided by the molar mass of gas A. We want to always define gas A as our fastest gas, therefore it's going to be our lighter gas. Keep in mind, the molar mass, the gas with the least molar mass is going to move faster. You want to define that as your gas A. That will make the calculations more simple. So let's take a look at an example. This first example says compare the rates of diffusion of hydrogen gas to oxygen gas. So if we take a look at the formula again, rate of gas A divided by rate of gas B is equal to the square root of the molecular weight of gas B. Notice these are opposite. If B's on top on one side, it's on bottom on the other, divided by the molecular weight of gas A. And we want gas A to be our lighter gas, so based on these formulas, we know hydrogen's molar mass is just 2.02 grams per mole, whereas oxygen's molar mass is 32.00 grams per mole. So we're going to define hydrogen as gas A and oxygen as gas B. And we're actually trying to we're comparing the ratio. So we're going to solve for this ratio here. So we don't really have anything to put any numbers to plug in here. This is what we're solving for. So I'm going to write this so it's more specific to this problem. So the rate of gas A, we're defining that as hydrogen, divided by the rate of gas B, who we're defining as oxygen, is equal to the square root of the molar mass of B. So B is oxygen, so we're going to plug in the molar mass of oxygen on top here. Notice these units cancel. Divided by the molar mass of A, which is just 2.02. So all you got to do here is you're going to say 32 divided by 2.02 and then take the square root of that. And that's going to give us the rate of hydrogen compared to the rate of oxygen is equal to 3.98. Now keep in mind this is a ratio, so the understood denominator is 1. So the way you interpret this is hydrogen's rate is 3.98 times faster than oxygen's rate. So what you would write is H2 is 3.98 times faster than O2. Okay, let's look at another example. Number 2 says calculate the molecular weight of a gas that effuses 1.59 times faster than CO2. So since this unknown gas that we're looking for, its molar mass, is faster, that means this is molecular weight of A is what we're solving for, because the faster gas is always A. And so if you kind of compare it to the last answer, the faster gas, so the rate of that, since we have a comparison, so the rate of A here is going to be 1.59, and we're going to define the rate of B as 1. Again, if you go back to the last example, when we finished, we said that hydrogen was 3.98 times faster than the oxygen. Well, here, this unknown gas is 1.59 times faster than gas B, which is CO2. And of course, we know the molar mass of CO2. We can calculate that. Carbon's 12.01, and then we have 2 oxygens. So we get 44.01 for his molar mass. So now we're ready to plug into the formula. So the rate of gas A divided by the rate of carbon dioxide, in this case, equals square root of the molecular weight of gas B, which is carbon dioxide, divided by the molecular weight of A, which is our X. So let's plug in. 1.59 plugs in for rate of A. Rate of carbon dioxide is understood to be 1. We just calculated the molar mass of carbon dioxide, 44.01, and this is going to be over X. We're solving for this. Now, in order to solve for X, we have to isolate it, and we have to, therefore, square both sides. Remember to get rid of your radical. You're going to have to square both sides. What you do to one side, you do to the other. So that's going to give me 2.53 equals 44.01 over X. Remember, when you square a square root, it simply gets rid of the square root. So it leaves us with 44.01 over X on this side. So now we have to solve for X by cross multiplying. That's going to give me 2.53X equals 44.01. And finally, we divide by 2.53. And that's going to isolate the X, which was our molar mass. And I got 17.4. And this will be grams per mole. Now on this problem here, we're going to go with least sig figs. Our least sig figs were 3. If you go back up here, we have 3 sig figs. So that's what determines we need 3 sig figs in our answer. Okay, so we'll do some more Grams per law problems in class. This is fairly simple to use as long as you got a calculator, since we do have square roots here.